Vex Robotics Team 134 presents a PID tutorial. There are many variables that your robot will encounter in trying to maintain a constant trajectory when throwing the balls. These variables are ball stiffness, battery voltage, and wheel speed. This video will address how to counteract the variables of wheel speed and battery voltage through the use of a PID control loop. PID stands for the three parts of this loop: proportional, integral, and derivative. The proportional term is a constant, Kp, multiplied by the current deviation from a desired speed, referred to as error. The integral term is a constant, Ki, multiplied by the total error accumulated over time. The derivative term is a constant, Kd, multiplied by the change in speed from one point in time to another. Here is an example of what a PID loop does. We will be creating the PID loop in Robot C. To begin, you must define the variables and set them to start the loop at 0. To begin the PID loop, you must first store the previously calculated speed as old speed in order to compare it with the new current speed. In the first iteration of the loop, this value will be 0. You must then store the current encoder value into clicks. Next, calculate speed by subtracting the previous encoder reading from the current one. There is no need to divide by time because the readings are taken with a constant interval of time. After this, store the current encoder reading into old clicks so that it may be compared with the next reading in the next iteration of the loop. Then, calculate the approximate negative derivative, which is the current speed subtracted from the old speed. This term will fight against any changes in velocity that the flywheel experiences. For the next part of the loop, set target speed equal to the desired speed, and then calculate the error. Add the error into the integral to sum all of the error this approach. Be sure that you establish a dead zone, however, in which if the absolute value of error is less than a certain trivial value, for example 1, integral will be reset to 0. Now, change the motor power based on the calculations given by the PID equation. This formula allows motor speed to adjust based on how far the speed of the flywheel is from target speed, along with using the integral term to ensure that it reaches its target value and the derivative term to preemptively resist any subtle changes in velocity.